Ladies and gentlemen, welcome to first tutorial, and today we'll be talking about limits, some amazing stuff. So first let's start with the notation. We have a function f of x, and when we want to figure out the limit, we write it like this. We write lim of function f of x in this case, where x approaches some certain value a equals to L. So this is the basics. This is the sorry guys, this is how the limit looks like, and it's not much harder than this to compute or to figure out the limit. So let's say we have an f of x of, let's change color, f of x equals, let's start with something easy, equals 3 over 2, where f of x is 3 over 2. Let's grab this. This is x-axis and y-axis, and we have 1, 2 here. This is 1, this is 2. So this graph looks like 3 halves, and it goes something like here, and this is a straight line. So we can see if we want to compute the limit, write it limit where x approaches infinity. At infinity, we're figuring out at infinity today, and where x approaches infinity of 3 halves is, and if we take a look at the graph, we see that as x is going to infinity, the the line is still at 3/3. So the limit of 3 halves where x approaches infinity is equal to the function itself, and this is 3 halves. And why is that? Because the function f of x is actually not related to the x, so as x changes, the y value stays the same. So this is a first theorem of, we'll say this is a first theorem. What's the best color? White. Okay, the first theorem is that the limit where x approaches any certain value, not only infinity, because at all certain levels, at all certain x, it is the same. So where x approaches a of a, let's say k is a constant. Let's write this down. K constant, sorry, let's say, oh, I'm sorry. K is a constant, and it is not related to x, equals k itself, like in this case. And this is going to be a very important theorem later on, and we'll actually use it in the next video. So in this video, actually already in the next example. So let's take a look at another example. This time we'll be having f of x being equal x minus 1 over x, and we want to figure out the limit of this function, limit of x as approaches infinity. We're going to be figuring out the limit at infinity today of x minus 1 over x. This is equal to L, which is equal to, and there is another a good way to calculate the limits is to divide or to extract the x on greatest power. In this time this is x on 1. This is the best to extract x on the greatest power from the numerator and denominator, and this would look like, this is a limit where x approaches infinity of x times 1 minus 1 over x, and denominator would be x 1. So as you can see, the x cancels out, the x's cancel out, and we get a limit. Let me write this quickly as possible. Limit of infinity equals 1 minus 1 over x divided by 1. And we can figure out easily that when x approaches infinity, I'm a bit confused. Where x approaches infinity, this element of the function is going to be more and more closely to 0, because the greater the denominator, the smaller the element itself is. So we can say that this is a limit where x approaches to infinity of 1 minus 0 divided by 1. And to go back, we had this first theorem saying limit where x approaches infinity of a constant is equal to a constant itself, and this is the same thing we got here. This is a constant, it's 1 over 1, and it's not related and relevant with with x, I'm sorry, so this is just 1. And this is actually the basics of infinity, and as you can see, it's not that hard to communicate, to compute them. So let's go with a slightly harder example, and this is going to be the last one today, and more coming in the next video. Let's calculate the limit of a function f where x approaches infinity, and function f of x being 3x squared minus 2 divided by 4x cubed minus 1. Okay, so we again extract the x in greatest power, and what we get is a limit of there's no line there, a limit of a function f where x approaches infinity, and the function f being with extracted x cubed. X cubed is the x in greatest power. X cubed, we get 3x squared over x cubed minus 2 over x cubed, and the denominator is x cubed times 4 minus 1 over x cubed, and this again cancel out, and some of the elements also cancel out, and what we get is a limit where x approaches infinity of 3 divided by x minus 2 divided by x cubed, and all divided by 4 minus 1 over x cubed. And as x approaches infinity, all these elements are similar to 1 over x, because if x is almost infinity, the 3 is nothing in relation to infinity, so it all cancels out. So what we get is we don't need to write limit anymore, because we will get rid of all the x's. This is 0 minus 0 divided by 4 minus 0, and that is just 0. And this is everything for today. We have calculated three limits, and just go back to the beginning, and we have this theorem, and we have figured out that if we have a limit of a constant, it equals to a constant, and if we had a x's on the same power, we actually get a positive value for that limit, meaning that oh, I'm sorry, I might have confused you. If we have, let's say we have x on power 1 on the denominator and this x on the same power in the denominator, we'll get a limit, will have its value over oh sorry, it's just the opposite, will be bigger than 0. This is the case where the power of numerator and denominator are the same. So the next example was where the power of numerator was smaller than the power of denominator, and we have gotten a limit being 0, which means that if a power of numerator is smaller than power of denominator, then from this follows that the limit of that function where x approaches infinity is equal to 0. So you can actually figure out from the very beginning that the limit of this would be 0, but you have to prove it on exams. You just can't say it's 0, because that is not a theorem. That is just for your mind only. You can like think, and if it doesn't come 0 out, you can say, oh, I have screwed up somewhere in between, and then you go back and you check, alright, maybe you have done something wrong here, and then you make it right. And that's it, guys. These are some good things to remember, and next time some more examples. I'm out.